Hello everyone, my name is Karina. I'm from Chemistry Education, 11 Maret University, and now I would like to ask you to study chemistry together. In this video, we will learn about hard, soft acid and bases. Okay, let's start. Before we talk about hard, soft acid and base, I'm going to recall about the definition of acid and base. How does one define acids and bases? In this chemistry, acids and bases have been defined differently by three sets of theories. One is the Arrhenius definition. For the first definition, an Arrhenius acid is a compound that releases H+ ions when added to water. These H+ ions form the hydronium ions H3O+ when they combine with the water molecule. This process is represented in a chemical equation like the picture below. In this reaction, hydrochloric acid or HCl dissociates completely into hydrogen H+ and chlorine Cl- ions when dissolved in the water, thereby releasing H+ ions into solution. Meanwhile, an Arrhenius base is a compound that releases OH- ions when added to water. The dissociation is represented by the following equation. In this reaction, sodium hydroxide dissociates into sodium and hydroxide ions when dissolved in water, thereby releasing OH ions into solution. Okay, for the next definition is from Bronsted-Lowry theory. In this theory, acids are defined as proton donors, whereas bases are defined as proton acceptor. Here, water molecule H2O donates a proton H+ to ammonia and H3, which accepts it, forming a positively charged ammonium ions or NH4+, and a negatively charged hydroxide ions or OH-. Therefore, H2O is a Bronsted-Lowry acid because it donates a proton, while the ammonia is a Bronsted-Lowry base because it accepts a proton. Also, OH- is called the conjugate base of the acid H2O, and NH4+ is called the conjugate acid of the base NH3. So that for the conjugate acid-base pair, you can see on the picture. Okay, next definition is Lewis theory. The Lewis theory of acids and bases states that acids act as electron pair acceptors and bases act as electron pair donors. This definition doesn't mention anything about the hydrogen atoms at all, unlike the other definitions. It only talks about the transfer of electron pairs. From the picture, we know that the reaction between ammonia and H3 and boron trifluoride BF3. Since there is no transfer of hydrogen atoms here, it is clear that it is a Lewis acid-base reaction. In this reaction, ammonia has a lone pair of electrons and boron trifluoride has an incomplete octet, since boron doesn't have enough electrons around it to form an octet. Because boron only has 6 electrons around it, it can hold 2 more. Boron trifluoride can act as a Lewis acid and accept the pair of electrons from the nitrogen in NH3, which will then form a bond between the nitrogen and the boron. This is considered an acid-base reaction where NH3 is base because it donating the pair of electrons to BF3, and BF3 is an acid because it is accepting those electrons to form a new compound H3 and BF3. Okay, now let's talk about hard, soft acids and bases. In 1963, Pearson introduced the hard, soft acid and base or HSAB principle. HSAB theory is a qualitative concept introduced by Pearson to explain the stability of metal complexes and the mechanism of their reaction. This theory allows us to predict which acids and bases prefer to interact. Recall the Lewis acid-bases theory can be applied to describe metal ligands interaction. Metal ions are electron pair acceptors and thus are Lewis acid. So when we discuss hard or soft acids in this course, we are discussing metal ions. Meanwhile, ligands are electron pair donors and thus are Lewis bases. When we discuss hard or soft bases, we are discussing ligands. Okay, now this is the hard-soft acid and bases theory. Hard acid react preferentially with hard bases and soft acid react preferentially with soft bases. And this theory, hard-soft acid and bases, is depending on Lewis acid-base theory that metal ions are electron pair acceptors, thus as Lewis acid, and ligands are electron pair donors, thus as Lewis bases. Softness roughly refers to the polarizability of an acid or base. The larger and more neutral any species, the softer it is. Conversely, the smaller and more charged a species is, the harder it is. And now we talk especially about hard acids and bases. In general, hard acids and bases have a high charge density, are not very polarizable, and form bonding interactions that are more ionic in nature. These atoms and ions tend to have high charge and or small radius. And this is the difference typical between hard acids and hard bases. For the typical hard acids are high positive charge, smaller ionic size, and early transition metal ions in the third series tend to be hard Lewis acid. And the typical hard bases are small anions and neutral molecules, and heteroatoms of the second row of the periodic table are typically hard, just like N, O, and F. And now we talk about soft acids and bases. In general, soft acids or bases have a low charge density, more polarizable, and form bonds that are more covalent in nature. These atoms or ions tend to have low charge and or large radius. And this one is the differences typical between soft acid and soft bases. For the first is the typical soft acids are transition metals with +1 charge, and transition metals in the second and third row of the periodic table that have +1 or +2 charge. Meanwhile, the typical soft bases are larger anions and neutral molecules. For example, I- and S2- are soft bases. And there is not only hard or soft acid and bases, but there is intermediate acid and bases. These are acids and bases with intermediate character between hard and soft. For example, 3-methylborane, Fa2+, and Pb2+ cations are intermediate acids. Meanwhile, pyrimidine and aniline are examples of intermediate bases. And this is the periodic table of hard-soft trend for acid and periodic table of hard-soft trend for bases. There are 3 types that are hard, intermediate, and soft. And this one is like binds with light, that hard acids interact more strongly with hard bases than they do with soft bases, and soft acids interact more strongly with soft bases than hard bases. Thus, the most stable complexes are those with hard-hard and soft-soft interaction. Okay, for the last is the principle of hard, soft acid and base. For the first is the large electronegativity differences between hard acids and hard bases give rise to strong ionic interaction. For the second is the electronegativities of soft acid and soft bases are almost same and hence have less ionic interaction. For example, the interaction between them are more covalent. And for the last is the interaction between hard acid and soft base are mostly polar covalent and tend to be more reactive or less stable. The polar covalent compounds readily form either more ionic or more covalent compounds if they are allowed to react. And I think that's all. Thank you for watching.